Last week, LlamaIndex released a very smart way of deduplicating entities after they use a model grid or LLM-based approach to create entities or triplets, entities, relationships from unstructured data to create a knowledge graph. The challenge earlier was that when you use a language model to create a knowledge graph, due to the non-deterministic nature of language models, so there are two challenges due to the non-deterministic nature. One is it creates different entities, different relations in multiple runs. So it is not consistent. Second is it creates duplicate entities or duplicate nodes also. The deduplication or disambiguation technique that LlamaIndex released yesterday, or I think this week, not yesterday, it partially solves the second problem where the language model creates duplicate nodes, and through this technique, we can deduplicate or remove some of the duplicate node entries. So this blog here in the LlamaIndex, they explain how they create the knowledge graph, right? And then finally, they also talk about the code that does the deduplication. Now, when I was going through it, what I noticed is that the deduplication part, which starts from here, right? It is not adequately explained how they do it in the code. So today I went into the code and understood how the deduplication occurs. It's a smart way because they use semantic similarity and Levenstein distance to check similar nodes, names of the nodes, and then identify duplicate nodes and then merge duplicate nodes together. That's what happens. But the code is very complex. So the query is complex. In fact, in the blog it says it took Michael Hunger, Eric Monk, and the author a couple of hours to perfect it, right? What I did is I took this query and spent some time to understand what it is doing, and I dissected that, or I make three parts of the code, right? So and then understood how each part is working, right? If you also see this code, the first part is where it is identifying the nodes that may be similar, the duplicate nodes, right? Then in the next one, it is so here, yeah, the combined result. This is where it is trying to. Okay, so the combined result also there are two, right? First, it tries to find out that within the identified nodes, right? Are there any duplicate similar nodes as well, right? And then when we look at the code, when I explain it with an example, it will be clear, right? One, it checks whether there are nodes that is repeated in subsequent list. And here they see if, again, like the similar nodes are duplicated or not. And finally, okay, this, they don't show it here. If I go to the code, the GitHub, finally, they merge the nodes here, the last part of the code is, so let me go here. This is where they merge the nodes, and when they merge a source and target node, they discard the properties of the target node, keep the properties of the source node, right? So this is the piece of code where they identify the similarity, then they find out if there are any duplicate entries, right? This is the code that I have dissected into 3 parts, and this is what we'll go through today. For that, first, let me actually create the graph first. So let me first ensure that I have everything deleted, so I don't have anything. So now let me go to the code. So I divided into 2 parts, the code. The first part is creating the knowledge graph. This one I'll not go through in details. This is basically, this is another thing I like about the Llama approach of creating the knowledge graph, where you can tell what entities you want to extract, then you can tell what relations you want to extract, then you can also tell which entities, like how these entities are related, how the entities and the relations are related to each other. For example, in this demonstration, the entities that I want to extract are person, location, organization, product, event. Relations are this, and for each entity, how the relations are connected to the entities, right? And then what we do is we use the schema LM path extractor to extract the this is what actually creates the object, the KG extractor object. And finally, using property graph index.from documents, where we pass the KG extractor and the document, the unstructured document. So I have 25 documents that I mentioned here. The triplets or the entity relationship will be then captured based on what I have defined earlier. And for each of the node relations, it will create a property called embedding and will embed using OpenAI. Because I use OpenAI here, right? GPT-4o, GPT-4o model is to extract the structure, the knowledge representation, and embedding, text embedding 3 small is what I'm using for embedding, right? So for each of these nodes, the names of the node will be, embedding will be created, right? And the embedding will be a property as part of the node. And at the end, what it does is it creates a vector index on that particular, on that embedding, right? It creates that, creates a vector index. I am not very sure if they use HNSW. I'll have to check that. I think they use probably the HNSW index only on the embeddings, right? So this is the first part of the thing, right? So this one will run first and see the knowledge graph, and then we'll go through this piece of code to see how they are deduplicating the nodes, right? So let me run this. It takes some time to run, and it's actually expensive. So if you are running it, be sure I already spent, I think I'm running it from last night, so to check different things. So I already spent almost $15 on this one. I run multiple times. So probably you'll not be spending that much if you run twice or thrice. And use GPT-4o. I was actually initially I was trying with GPT-4, which that's why also like the cost went up for me, right? So it is, the other thing that I noticed is there was a bug, and the bug was because and the bug, I'm not sure if it is in Neo4j or the LlamaIndex. So in here, I had to I Let me check. I commented out the log. Yeah, this is what I commented out in. So this is from Neo4j package, the Neo4j SDK in the sync. This is part of the sync IO bolt 5.py, right? For some reason, this log object was not instantiated. So if there is a exception that happens in while creating the nodes relation, so in LlamaIndex, they're passing it like they're because in some cases there may not be entities and all, right? But if the exception happens when it comes here, it was not able to find a log object, right? So to make it work for temporarily, I commented this out in the Neo4j sync IO bolt 5 dot underscore bolt 5.py. Did not get a chance to see why it is happening, but now but with that, like I was able to create the knowledge graph. So now the knowledge graph has been created. If I go to the knowledge graph, if I run it, you'll see that it is now created. It's a okay. So let me do all the things, including the relations. So you'll see there will be multiple. Oops. Okay. Yeah. So now, yeah, so many graphs got created. If I, yeah, so I'll take one of them. Right. So this, all this are extracted from the unstructured data. Now let's actually look at the second piece of the code, which is a deduplication. This is where I spent a lot of time, right, to understand how they're deduplicating. Okay, so the first part. So this is a function that is written to run the cipher queries so that I don't have to duplicate this piece, right? So create as a function. You give a query cipher query, it will execute it, right? So the first part of the query. So as I said, like I dissected this piece of code into three parts, right? The deduplication part, and this is what I'm going through right now. The first part identifies all nodes that are similar, uses cosine with cosine with a threshold. For the demonstration, I used 0.8 as a similarity as a threshold for the cosine score, right? So the identifies all nodes that are similar, right, where score greater than this 0.8, and also nodes that are n Levenstein distance apart. So I used 5, right? So it uses epoch.text.distance, which is nothing but measuring the Levenstein distance between the nodes with a 5 words apart, right? That's what this piece of the code is doing, right? It is identifying nodes that are similar, nodes that are 5 Levenstein distance apart. The first collection here, this collection here, aggregates the similar nodes in a list from this, right? So there will be multiple nodes, right? So this first collection aggregates those nodes. The second collect aggregates the name of nodes within each node list into a list of lists and expose results. So basically, after this runs, all similar nodes will be grouped together. So let's say I have node A and node B, if they are similar. So node A comma node B will be one group. Let's say node B, node C, node D are similar. Node B, node C, node D will be another group, right? This is what we get back from here, right? That is the first part. The second part, and when we'll run it, it will be more clear because I have printed the output from each of this other step, right? Then I'm flattening these results for the next part. What the next part is doing, right? Okay. Let's understand with an example. So from the first part of the code, right, we get this as the output. So this part, right, if I have node A, node B, node C, node D, node E, I get back an output like this, where node A and node B are similar, node B, node C are similar, node D, node E are similar, node G does not, it's standalone, there is no other nodes that matches this node G, right? The second part, this goes as an input. So if you see, this is the input, and we are doing an unwind. What unwind is doing is, it is unwinding this into a row, right? Each component in the list becomes a row, right? Node A, node B is row, node B, node C is a row, right? And then we do a reduce call, right? What it is doing, right? So for each results, it performs the following operations, right? When within this, right? So for each of this row, what it is doing is, so first iteration, I have this, right? Node A, node B, right? The accumulator starts with this, right? This is the accumulator, right? And loop through the results. So index 0, right? So here, if you see, accumulator index 2 in range 0 to the results index, right? So what is the index 0? So this is index 0, this is index 1, 2, 3, 4, right? So for each of the index, right? So it checks the result, whether it is, so index, whether it's same, right? For example, for the first one, right, it will be same as index 0, because this is the uh, index 0 item. So when I loop through these results and match it with this, the first one will be same. Node and node B are same. So we skip it. Next, I go to the next index, right, which is this. I match this with this, right? And here I see there is an intersection. So node B, node C is my index 1. I'm matching it with my first index, right? Node A, node B, and there is an intersection. There is node B, node B. So I do an union and I combine this into node A, node B, node C, right? That's what is happening here. If you see, for the reduce for each of those rows, it is checking whether each row, is it equal to the all the indexes, all the items that I have in the results thing, right? And then if it is not equal, and if there is a intersection, if the intersection is greater than 0, then I combine them, right? So as we saw here, right, node A, node B, right, intersects with node B, node C. So the final one became node A, node B, node C. It does this for each and every row, right? So the final result, then the combined result, final combined result, we get a, so here is one deduplicated node that we get, right? Node A, node B, node C, node D, node E, node F, and node G, right? I get it like this. That is the first piece, right? That is the second part of the query is giving me this, right? Now let's go to the third part. What is the third part doing, right? So let's say in my previous output, right? If I got an output like this, node A, node B, node C, node D, node E, node F, node A, node B, right? Node A, node B is contained here also, right? So these and this needs to be combined now, right? That is what the third part is doing, right? So what it is doing is, given this input, iterating over each index, right? So first index is this. No list fully contains this three, right? None of the items in the list are containing everything, node A, node B, node C, right? So you include this in your final result. Node D, node E, node F. No list fully contains this, right? If you see, none of the contains, right? So include this also in the result. Node A, node B, right? If you see node A, node B is contained here, right? So exclude this list from the result because you have already considered it here, right? Then the node G is not contained anywhere, so include this. Node D, node E is already part of node D, node E, right? Exclude this from the list. So finally you have this set of nodes, right? That node A, node B, node C are similar. Node D, node E, node F are similar. Node G are similar, right? Till this third piece, we got a unique set of nodes which are similar to each other. This three are similar to each other, this three are similar to each other, and this does not have, this is a single one, right? Now, next, so this is what the query part 3 is doing, right? The last part, the part 4, is where all the magic is happening. This is where the merging is happening. How is the merging working, right? So this is the query for the merging, right? So here this was the output from the previous one. So for each item in this list, right? I'm taking the first one first, right? I'm unwinding it. So it will expand to node A, node B, node C. Then you match it with the entity, the name, the property name. You ordered by the size of the name, right? So that why the order by in a descending order name is done, so that the node with the most descriptive name becomes your source node. Sorry, the target node. The other two nodes should get merged to it. You want to keep the name of the node with the most descriptive name. That's the idea. And finally, when you do a merge node with these nodes, node B, node C gets merged to node A. And since we said discard, right, the properties of node B and node C are not carried. Node A keeps its properties, but node A, node B, node C now becomes node A, right? This is how the deduplication is happening, right? This is what this query, this is the deduplication query, right? Whatever I just explained, right? This is what this is where the merging nodes is happening, right? And finally, you have a deduplicated graph now. Now it is not 100% accurate. I have seen in some of the cases, because it's again based on your score, right? Semantic score and your Levenshtein distance. So if some of the nodes are duplicated and the Levenshtein distance is more than 5, or the semantic match is less, right? You still may have some duplicated nodes, but it is still better than nothing. So let me run this now, and then we'll go back to our here, right? And then we'll see, right? So okay, first let me do this. First, let me comment this part, run it without deduplication, and then we'll come back and uncomment it and see the difference. So now I'm running it without merging. So let me run this. So, okay. So these are the duplicated ones, right? Epic Games, Bank of America Corp. These are the duplicate nodes, right? Let's actually verify this as well. So I have this. Oops. Let me take this. Oops. So Epic, right? So if you see, there are two, right? Epic Games, Epic, name Epic, and Epic Games, right? Next, look at the Bank of America. Bank of America. I have two again, Bank of America Corp and Bank of America. Let's look at Star Ocean. And this time we have 1, 2, 3, right? So here, no, 1, 2, right? This is where, okay, so let's look at this, right? Star Ocean, second story logos. Star Ocean, second story are logos. Star Ocean, first departure, right? That did not come here, right? That's what I'm saying, that it is not 100% accurate. Then the next one is the second story R. This one came in. And the fourth one is Star Ocean first departure, right? Let's see the Star Ocean first departure came in. Yeah. So yeah, it actually did it here. So Star Ocean first departure, it combined. Logo link. Let's see the logo link. Logo link. Right. So here we'll see two, logo link and logo linked. Right. This is also came. Then support NA square. Support NA square. This should also we'll see support NA square and the other one, right? This two also came in, right? And FASTag. This is a problem. You see this number. I can have uh, duplications here, right? But here it will deduplicate this also, because I can have a phone number 409-212-4664. I can have another one 409-262-4665. Right? But if I my Levinson distance is 5, right? I probably will deduplicate them, right? So this is another limitation right now with numbers. But let's look at the FASTag. So FASTag also, there are, we'll find two. Right? Yep. So let me actually copy it here. After we will run it again with the last part. We'll execute the fourth part of the query and we'll see how it looks like. Right. Let me uncomment this. So we have 1, 2, 3, 4, 5, 6, and 7, and 8. 8 pair of nodes that we need to deduplicate. So let me run this now. At the end, I should have 8 nodes. So 8, right? Total 8 nodes got deduplicated. Now let's run this again, right? Let's see what happened. First tag, I have only one right now, which is good. Epic. Oops. I should have only one. Yeah, I have only one. And you see, the one with the descriptive name, Epic Games, has been kept. The Epic one, the name was Epic one, that was removed. We'll see one more because all these things are same, and then I'll close this recording. Right. So Bank of America. Here also you'll see the Bank of America Corp has been kept because that has the most descriptive name, right? And now if I do it for all these things, I'll see that only one node finally remains. Right? That's all I wanted to show as part of this. Right? This is really a smart way of deduplicating or disambiguating the deduplicating the nodes after we use LLM. But this, and if we combine with an entity resolution type of thing, I think it will be very, very powerful. Thank you.